Hi and welcome to the video. In this one we will cover how the analytical solution to a state space model can be calculated. We used this solution in the last video to speed up our simulation of the discrete implementation of a PID controller. This video is divided into the following sections. First, we look at what we are calculating and why. Afterwards, we briefly cover how to calculate the required matrix and vector. Then we look at a possible implementation in code, and I show you a simulation example to highlight the accuracy of the method. Finally, we close with an outlook. What we do is look for a direct solution of the state space representation to calculate our state at the next controller cycle. So we are looking for a different representation of this continuous state space model. The solution we are looking for comes down to the solution of this integral. But instead of calculating the integral itself with numerical means, we instead calculate a representation looking like this here, where we solve it with a simple matrix multiplication. We assume that the input uk is constant over the control interval, which is the case for the discrete controller action, and the matrix AD and vector BD being used are also constant. While the solution to the matrix AD and vector BD are calculated numerically, they still represent an exact solution. Therefore, the calculation result can be a lot more accurate than that of a simulation using an ODE45 integrator, especially for larger time steps TA. Depending what algorithms are used to calculate it, there are obviously limits, but in theory, this is the exact solution. This calculation is not only useful to speed up a simulation of a system running on a discrete time interval, like we had in last month's video. Another application of the model we calculate here is in the application of observers for state reconstruction or when designing state feedback controllers. An observer is a powerful concept in control engineering, and we can use the discrete model calculated here as basis, so I wanted to cover the calculation. The equations to calculate AD and BD look like this here, where we use the Matrixexponential function. Be careful, however, this is not the same as just applying the exponential function to the individual entries of the matrix, but this is a multi-step process, especially when calculating by hand. We have to differentiate between two cases here. The first one, where the matrix A is fully diagonizable, and the second one where this is not the case. If the matrix A is fully diagonizable, the calculation of AD comes down to be as follows. You first calculate the eigenvalues and eigenvectors, then create a matrix big T containing the eigenvectors and a matrix big lambda containing the eigenvalues on the diagonal. Then you can apply the exponential function to every individual eigenvalue like this. You can do this because this matrix big lambda is diagonal, and for such a matrix, its Matrixexponential function is just the solution of the individual exponentials. Be careful, this is only possible because the matrix big lambda was diagonal to start off with. If you want to know why this is, there is a video by 3 Brown 1 Blue with a pretty intuitive description. Check the link in the video description. And at the end, the Matrixexponential of our original matrix A comes down to multiplying everything together like you see here. AD is then just the result here with the controller cycle time TA instead of T. So the step size for one discrete step, and BD is the result of this integral. For the second case, where the matrix is not diagonizable, you first have to calculate the Jordan normal form for the matrix A. Afterwards, you can calculate the solution for every Jordan block, and this will give you the solution of the Matrixexponential function. Doing this by hand is horrendously tedious, however, and you are usually better off doing it numerically, like I will show you in just a minute. For demonstration purposes, we use the model from last month's video. This here is our system with the equation of motion leading to this state space model. The parameters are given over here as well. Later on, we will compare the simulation results to the analytical solution of the differential equation of motion. Let's move this out of the way and look at the code. After our usual housekeeping, we define our continuous state space model. First the parameters, then the matrices and vectors. We then use this command here to create our state space model object. Afterwards, we define our time step. For this example here, we will use 1 millisecond. The calculation of AD and BD can simply be done with this one line here, where we calculate the discrete model from the continuous, with the time step provided. Completely independent if the system is diagonizable or not. Yes, a lot easier to do numerically than by hand. To check the result, you can compare the resulting matrix AD from this calculation with the direct calculation using the Matrixexponential function. I decided to use the transformation with C to D because we get both AD and BD in one step. To show the accuracy of the calculation, we run different simulations and compare the results. We start by defining our initial state, a sample input and common time series for the results, and calculate the result of the analytical solution. Afterwards, we run the ODE for 5 integrator and interpolate the results using the same time series from before for plotting. Later on, to show the accuracy of the discrete calculation, I decided to include 2 versions of this calculation. In the first one, we are using the time step of 1 millisecond calculated previously, and we are calculating from one point to the next, one after another. In the second version, we are calculating a different matrix AD and vector BD for every step by adjusting the time step used for calculation. So we are always calculating from the initial values, just using larger time steps. Afterwards, we plot the results. Speaking of, here they are. First, we plot the result of the analytical solution, the results of the continuous simulation, and of the 2 discrete calculations. Because they all look identical and we cannot see a difference, we plot the error between the analytical solution and the other 3 versions down here. The error between the analytical solution and the solution with the ODE for 5 integrator is naturally larger than the error of the other solutions. We can decrease the error if we have to by forcing the integrator to take a smaller time step. You can remove those parts and comments of the calculation in the code and try that if you are interested. If we adjust the scaling of the axis, we can see the error of our 2 discrete calculations. Even though we used numerical methods to determine the matrices AD and vector BD, the error between the analytical solution and the 2 discrete solutions is remarkably small. The error is naturally larger if we calculate from one step to the next consecutively, but I think it is impressive just how small the error is. We can then use this discrete model as base to design a controller or observer in a follow-up step, but that is the topic for another video. Okay, and that is it already. We covered how you can calculate the discrete model from a given continuous one. First, how you can do it by hand, and afterwards, how you can solve it numerically. You can find a link to the code in the video description as always, if you want to play around with it yourself. I am not entirely sure what the next video will be. I see 2 options, covering how to derive the calculation of AD and BD, and showing what we calculate with the Matrixexponential function, or covering how the short or normal form that is required for systems that cannot be diagonalized can be calculated by hand. I'm not sure yet. Thank you very much for watching. Like, comment, share and subscribe. Bye for now.